Section: Introduction. In this section, we discuss the emergence of large language models, LLMs, as adaptable foundations for various AI applications, particularly in handling complex tasks that require multi-step reasoning and tool usage. Their ability to generalize across tasks with minimal adjustments has led to rapid advancements and widespread use. However, the main goal of language modeling, creating unstructured sequences of tokens, limits context windows and complicates fine control over internal states. This creates challenges for state-of-the-art LLMs, particularly in maintaining long-term reasoning and managing intricate workflows, which are essential for developing robust applications that require significant memory. Neural networks produce natural language in a linear fashion, and architectures like recurrent neural networks, RNNs, and transformers face restrictions due to token limits and memory capacities. For instance, standard models like DeepSeek R1 can handle up to 128,000 tokens, but real-world tasks often need longer reasoning spans, especially when LLMs interact with external tools. Some specialized models, like the compressive transformer, attempt to extend context by compressing past information, but they still struggle with balancing memory accuracy and computational efficiency. To address the limitations of working memory, developers often break down complex workflows into multiple modules, known as multi-agent architectures, where each model instance tackles specific subtasks. While these frameworks can simplify problem-solving in specialized domains, they introduce significant overhead when dealing with more arbitrary tasks, as agents do not inherently manage coordination or control flow. This requires developers to manually handle context management and communication between agents, which complicates integration with external tools. We believe that reasoning is not a straightforward process. It is structured recursively, similar to language, as seen in our everyday experiences. For example, in programming, we focus on nearby lines of code and remember function inputs and outputs without needing to recall every detail of completed functions. Inspired by this, we propose a new approach to overcome the context and representation limitations of traditional neural language models. We conceptualize a reasoning trajectory as a recursive tree of subtasks, where higher-level nodes represent complex tasks that break down into simpler subtasks until reaching a straightforward task at the leaf node. Our hypothesis is that when processing an intermediate task, we do not need to consider all previous subtasks. By eliminating irrelevant subtasks, the model can concentrate on a selective, working memory. This allows an LLM reasoning over pruned trees to avoid attending to all context tokens, providing richer contextual information compared to traditional linear models. By breaking down large workloads into subtasks, we can significantly reduce the number of context tokens and memory entries needed during reasoning, enabling extensive long-term reasoning while keeping track of instructions and important context. This results in improved decoding speed and lower memory costs. In this paper, we present our implementation of this concept, which includes two main contributions. First, we introduce the Thread Inference Model, TIM, a transformer-based LLM that recursively breaks down complex tasks, follows subtask instructions, and combines outputs from subtasks. TIM also learns to effectively utilize multiple external tools within these subtasks to complete complex workflows in a single inference call. By creating a structured reasoning trajectory, TIM can easily identify subtasks, tool parameters, and the hierarchy of recursion. Second, we developed TIMRUN, a specialized inference engine for TIM. This engine recognizes the structure of reasoning during inference, dynamically frees up memory used by unhelpful subtask states, and reuses that memory for further inference. The structured reasoning approach simplifies tool usage, as TIMRUN extracts tool information during inference, calls tool servers, and updates the memory cache with tool responses without interrupting other requests in the same batch. With TIMRUN, TIM achieves significant breakthroughs. It enables virtually unlimited long-term reasoning beyond token limits, allows efficient single-model reasoning for complex tasks with improved decoding speed and memory efficiency, and facilitates the creation of agents in a streamlined manner, equipping TIM with a toolkit, launching one-model inference, and receiving a coherent reasoning trajectory. Section Summary. In this section, we discuss the limitations of large language models, LLMs, in handling complex tasks due to strict context window limits and propose a new approach that models reasoning as a recursive tree of subtasks. Our implementation, the Thread Inference Model, TIM, and its engine TIMRUN, allows for efficient long-horizon reasoning and improved memory management, enabling a single model to effectively manage complex workflows and tool interactions. Section: Thread Inference Model, TIM. In this section, we present the Thread Inference Model, TIM, where we conceptualize reasoning paths as recursive subtask trees and train a transformer-based model to understand this structure. We begin by outlining the enhanced thread structure we developed for reasoning, followed by our data synthesis and model training processes. In our design, we define a task as the fundamental unit of reasoning. Each task includes a thought process, optional tool usage, a possible list of subtasks, and a conclusion. The purpose of these components is as follows. The thought process identifies mistakes from previous steps, evaluates current progress, and plans future actions. Tool usage allows for the optional invocation of a specific tool by generating its input and processing its responses. Subtasks can be created if the task requires multi-step reasoning, but their details remain hidden for efficient context management. And the conclusion summarizes the tool results and the outcomes of the subtasks, providing enough information for future reasoning tasks. All tasks in our reasoning tree follow the same structure. Thread 2 improves upon the original thread reasoning framework in several ways. Unlike the initial version, which required each subtask to have its own copy of the higher-level task instructions, Thread 2 allows subtasks to access a shared working memory that includes the system prompt, user input, and all relevant tasks. This change enhances efficiency by enabling end-to-end inference with just one call to the language model. For subtask pruning, we can easily extract subtasks and their hierarchy, allowing us to simplify the reasoning context without needing external summarization models. We believe that to process the current task, we only need to reference the thoughts and conclusions from previous tasks at the same or higher level, while lower-level subtasks can be ignored. However, to ensure accuracy, we maintain a fixed-size stack for subtasks. When a subtask list is completed, we add it to the stack, and if the stack exceeds a certain size, we remove the oldest list. In terms of structure generation, instead of using special tokens for structure, we can efficiently decode the reasoning process as a JSON dictionary. This allows us to handle multiple tool calls in a single decoding pass, reducing overhead associated with traditional message list designs. By extracting parameters as a dictionary and waiting for tool responses, we can extend our cache without the need for multiple calls to the language model. For training, we post-train a small open-source model using a synthetic dataset to validate our main hypotheses: that subtask pruning does not compromise reasoning accuracy and that managing the cache does not introduce additional computational overhead. We create a synthetic training set for the Qwen 3-8b model, generating questions from various categories and assigning tools accordingly. We synthesize tool responses as part of the JSON generation task, which allows us to train the model using Llama Factory. Additionally, we implement reinforcement learning on the fine-tuned model using remaining questions from a dataset, maintaining the JSON structure during sampling and providing rewards based on the accuracy of predicted answers. Despite the noise in our training dataset, we find that reinforcement learning can still enhance the model's performance. Section Summary. In this section, we present the Thread Inference Model, TIM, which utilizes a recursive subtask tree structure for reasoning, enhancing efficiency by allowing end-to-end inference with a single language model call. We also describe our data synthesis and training processes, including the creation of a synthetic dataset and reinforcement learning to improve model performance while managing subtask pruning and tool interactions effectively. Section: TIMRUN, the inference runtime for TIM. In this section, we introduce TIMRUN, the inference runtime designed for TIM. TIM's structured output opens up new possibilities for improving reasoning performance and accuracy, but it also brings challenges for deployment. To maximize TIM's capabilities and tackle the issues posed by the Thread 2 reasoning framework, we created TIMRUN specifically for the TIM model. The main distinction between TIM and traditional agents is in how they handle input and output windows, which creates practical deployment challenges. Traditional agents update message lists gradually, with the underlying language model encoding them as part of the input. In contrast, TIM processes the entire reasoning in the output window, which is challenging because many language models have stricter limits on output compared to input. For example, while Qwen 2.5 allows for 128,000 tokens in input, it only permits 32,000 tokens in output. To facilitate long-term reasoning that goes beyond this output limit, TIMRUN needs to efficiently reuse GPU memory and positional embeddings during output generation. We also emphasize the importance of subtask pruning for effectively implementing TIM and maintaining long-term reasoning. The central idea is that the model only requires outputs from prior tasks at the same level of abstraction, allowing it to discard unnecessary internal details. We illustrate this with a simple analogy: how to put an elephant in a refrigerator. 3 steps. Open the door, put the elephant in, then close the door. To apply this principle, TIMRUN uses a pruning buffer, which temporarily holds a small set of subtasks that can be pruned while ensuring that information flow remains intact. As TIM decodes a task, TIMRUN actively removes the key value states of completed subtasks from GPU memory. While this could theoretically happen during the forward pass, it often leads to extra computation and delays. To reduce the overhead of managing GPU memory, we handle the key value cache and prune subtask tokens before inference using paged attention. We set the page size to 1 since each request in a batch requires different pruning. The pruning process is implemented with Triton, and inference with a page size of 1 is sped up by flash infer. When we have a token sequence and a key value cache before pruning, we can remove certain tokens based on our pruning rules. Although we can recycle memory from pruned tokens, TIM cannot decode more tokens beyond the output limit because the positional embeddings need to be re-encoded. Thus, we must re-encode all tokens after the pruned subtasks to reassign their positional embeddings. Even though this re-encoding increases computation, it is done in parallel by GPU kernels, so overall throughput remains efficient. By properly decomposing subtasks, TIM can iteratively reuse GPU memory and positional embeddings in the output window, enabling long-term reasoning beyond the output limit. We also address the issue of excessive token costs associated with tool use and multi-agent frameworks. In autoregressive language model generation, each inference consists of 2 stages, prefilling and decoding. Prefilling encodes all input tokens at once, storing their hidden states in the key value cache, and generates the first output token. After this, only new tokens are processed for further predictions. However, many LLM APIs require resending the entire message list for each new user turn, leading to redundant costs. To optimize this, inference engines cache hidden states for previous tokens, but token retrieval and network transmission still add overhead. Moreover, commercial LLM APIs often charge for encoding cached tokens, resulting in developers paying multiple times for the same tokens. In multi-agent architectures, treating each reasoning step as a new request can lead to significant cost complexity. Tool use exacerbates this issue, as each tool call incurs re-encoding charges for all previous context tokens. TIMRUN solves this by initiating tool calls directly within the runtime, reducing inter-module communication and streamlining agent development. With TIM structured generation, when TIM outputs a tool result, TIMRUN extracts the necessary parameters, forwards the request to the external tool, and appends the tool's response to the ongoing reasoning process. This design ensures that each token in the reasoning chain is sent to TIMRUN only once, minimizing communication overhead and supporting typical chatbot applications effectively. Section Summary. In this section, we introduce TIMRUN, an inference runtime designed to optimize the deployment of the TIM model by addressing challenges related to output window limits and memory management. We also discuss subtask pruning to enhance long-term reasoning efficiency and detail how TIMRUN minimizes redundant token transmission during tool use, significantly reducing computational costs. Section: Experiments. In this section, we present the benchmark results of our model on reasoning and research tasks. Our experiments reveal several key observations. First, using a working memory instead of calculating attention weights for all context tokens does not negatively impact reasoning accuracy. In fact, removing irrelevant context can enhance reasoning accuracy and reduce errors in language models. Second, TIMRUN maintains high processing speed even with heavy memory access and manipulation. For our reasoning evaluation, we tested TIM models on various benchmarks, including MATH 500, MMLUSTEM 500, AMC 2022, AMC 2023, AMI 2024, and GPQA Diamond, to assess their STEM knowledge and reasoning skills. The initial results are summarized in a table. We compared TIM's reasoning accuracy across different infrastructures. When using SG-Lang, TIM produces structured outputs without pruning subtasks. In contrast, TIM combined with TIMRUN incorporates subtask pruning and memory management during decoding. Our findings show that subtask pruning in TIMRUN does not harm overall performance. Instead, keeping only the most relevant information in the memory cache improves TIM's performance on many tasks. We observed that TIM achieves its reported performance while using less than half the memory slots needed for the complete output sequence. Notably, the maximum memory cache length is typically reached only once during generation, with smaller sizes for most other steps. Thus, the reported memory savings represent a lower bound on the efficiency gained through TIM and TIMRUN. In our research, we found that large language models enhanced with external knowledge often need to create search queries for information retrieval. Traditionally, this process involves complex workflows for generating queries, invoking tools, and aggregating responses. However, TIMRUN simplifies this by efficiently extracting tool parameters, invoking necessary tools, and directly appending raw responses to the output. This means developers no longer need to create complicated workflows. TIMRUN handles multi-step tool usage as a straightforward API call. We evaluated TIM models on research tasks without relying on any agent framework or complex prompts, using benchmarks like BrowseComp and Datacommons QA, which require multi-step information retrieval and reasoning. For Datacommons QA, we provided the model with a search tool to interact with Datacommons and assessed its performance on 140 benchmark questions. Our main baseline, Thread, uses a specific prompt with over 4,000 tokens and includes detailed examples for Datacommons queries. Other baseline methods also depend on few-shot prompting with tailored examples. In contrast, TIM only needs a brief system message and essential tool information, such as descriptions and input parameters. We note that the model was not trained on the specific Datacommons tool used, and we plan to explore performance improvements through fine-tuning in future experiments. The results indicate that TIM generalizes well to new tasks not seen during training. Compared to baseline methods, TIM is more efficient in three main ways. It eliminates the need for detailed few-shot examples, reduces computational overhead by avoiding lengthy prompts, and automatically processes tool responses without requiring custom logic from developers. BrowseComp is a challenging benchmark for deep research agents, requiring the decomposition of input, tool usage for information retrieval, and validation of findings. Traditionally, these tasks need agent-based systems that manage long reasoning chains and aggregate multiple tool responses. We developed a system that allows GPT 4.1 to generate JSON structures for TIM using a generic system prompt. While TIM Large is more capable than our smaller model, it is less efficient as it is not served on TIMRUN. We used TIM-Large to validate TIM's new reasoning pipeline. Similar to our Data Commons QA experiments, we did not use an agent framework to manage contexts. Instead, we implemented subtask pruning for context efficiency. The results for large language models without post-training on deep research tasks are presented in a table. TIM-Large significantly outperforms GPT-4o with browsing capabilities and achieves performance comparable to the React agent built on DeepSeek R1, a strong reasoning model. These results support our hypothesis that a model managing its own context by breaking down subtasks and pruning memory can match the performance of more complex agent implementations. Notably, even TIM-8b outperforms GPT-4o in end-to-end browsing scenarios when handling research tasks. Section Summary. In this section, we report that our TIMRUN model maintains reasoning accuracy while efficiently managing memory and improving performance through subtask pruning, allowing it to outperform traditional agent-based systems in complex research tasks without requiring extensive prompts or bespoke logic. Our experiments demonstrate that TIM generalizes well to novel tasks, achieving high efficiency and effectiveness in multi-hop information retrieval and reasoning. Section: Efficiency and Scalability. In this section, we explore the efficiency and scalability of TIM. We highlight how TIM can dynamically reduce subtasks and keep a working memory with less than half the context tokens, which opens up new ways to enhance the performance and memory efficiency of large language model (LLM) serving systems. Our experiments focus on two main questions. First, whether the intensive manipulation of the key value cache adds extra computational costs, and second, if we can decode larger batches with a smaller working memory when we prune the context. Regarding memory management, we initially thought that reducing the key value cache would lower the computational costs of the attention mechanism. However, our experiments using Hugging Face and PyTorch showed that the overhead from managing memory actually exceeded the benefits of a shorter cache. For instance, with a batch size of 1, the standard decoding using Hugging Face's eager attention processed 22 tokens per second, while decoding with cache pruning dropped to 18 tokens per second, indicating nearly a 20% decrease in throughput. These early findings suggest that managing memory for cache pruning may be less efficient than simply computing attention over longer contexts. When it comes to TIMRUN, we found that context pruning and the attention mechanism involve a trade-off. While pruning can speed up attention computation, it also adds memory overhead. We discovered that TIMRUN effectively balances these factors. Despite the need for structural checks and frequent memory access, it improves throughput at the same batch size. During the AMY 2024 challenges, we tested various pruning buffer sizes and compared their throughput with a batch size of 30. Our results showed that when we kept fewer than 2 subtask lists in the pruning buffer, the key value cache in GPU memory remained compact enough. In this scenario, the time saved from attention computation through subtask pruning outweighed the extra memory access overhead, resulting in higher throughput than the baseline system. However, as we increased the pruning buffer size and pruned fewer subtasks, we faced more memory management overhead without enough computational savings, which led to reduced throughput. We also included an 80% throughput line in our plot to represent the results from memory access during the model's forward phase. Overall, TIMRUN outperformed both naive memory operations and the strong SG-Lang baseline. Additionally, we found that TIMRUN can directly invoke custom tools from the runtime, avoiding the need for client or developer intervention. This method simplifies development and enhances inference scalability. By calling tools and encoding results within the runtime, we avoid several overheads. For example, we reduce network transmission delays since tool parameters don't need to be sent back and forth. We also eliminate the need to cache tokens and manage their states. Most importantly, TIMRUN's subtask pruning mechanism boosts inference efficiency by discarding previous tool responses along with completed subtasks. Our experimental results support this hypothesis. We evaluated the TIM-8b model on both SG-Lang and TIMRUN using browse comp tasks, analyzing the link between average throughput and the number of tool calls. As anticipated, Glang's throughput declined sharply with more tool calls due to the increasing complexity of context and token cache from reasoning steps and tool responses. In contrast, TIMRUN maintained relatively stable throughput even as tool usage increased, thanks to its automatic context management. This allowed the TIM-8B model to perform well on the Browse Comp benchmark without requiring any agent framework or task-specific post-training. With subtask pruning, TIMRUN can handle over 30 tool calls in a single inference.